Here I am looking for a description of a plane that contains 3 points as an algebraic equation. So I want to find an algebraic equation whose solution set is the plane containing these 3 things. And this is where I'm going to start. The plane that contains these things also contains some directed line segments. I'm going to think of those directed line segments as vectors to help me get a normal vector. So that is to say, if I have a plane, I'll draw in blue, looks about like that, and it has 2 directed line segments in it that look like this. Okay, so both of those red directed line segments are meant to sit in the blue plane. Then there is something normal to both of them. Normal to, so let's see, 90 degrees to that and 90 degrees to that. And I am looking for that guy. And so I'm going to obtain it by the cross product of these 2 things. So let me figure out what those 2 line segments are. Those 2 line segments I could make PQ, which is a vector with, let's see, P to Q. So I want 2, 0, and 2. And I want to subtract, so that was Q, I want to subtract 1 from there, subtract 1 from there, and subtract -1. So the components of Q minus the components of P, which this comes out to 1, -1. 2 minus -1 is 3. And let's see, I could also do, say, P to R. PR, so I want to put components of R first, 0, -2, and 1, and I subtract the components of P, 1, 1, and -1. That comes out to a nice round -1, -3, 2. Okay. Connect this with an AND. So those are 2 line segments, and so I can draw that, right, these 2 line segments, and I want to find something normal to that to get a vector normal to the plane. And so has normal vector. I want to do PQ cross PR. So I certainly could have done QR also up here, but I actually only need 2 directed line segments. I don't need a third. This would be, oh, you know, I'm going to jump straight to the determinant trick notation. I hat, J hat, K hat. The components of PQ are 1, -1, 3, and PR, -1, -3, 2. And the first component is I ignore the row and column of I, and I get -1 times 2, it's -2, minus -3 times 3, so that's -2 plus 9. -2 plus 9 is 7. Next, I ignore the row and column containing j, and I have 1 times 2 minus -1 times 3, that's 5, but I am always supposed to put an extra negative sign in that middle component. So 1 times 2 minus -1 times 3, that's 5, I put a negative sign, good, just double checking myself. Okay, 1 times -3, that's -3, minus -1 times -1, that's 3 minus signs, so overall -1, so -3 minus 1 is -4. Okay, and next I'll talk about an arbitrary point on the plane. If x, y, z, the point, is on the plane, then the normal vector 7, -5, -4, dotted with x, y, z. I mean, there is a slight difference between a point and a vector. Just want to remind you of that. I have promoted this point to a vector by thinking of the vector that goes from the origin to the point x, y, z, a directed line segment. Okay, so the idea of a plane is that the dot product of any point on the plane with the normal vector to the plane is the same. So this should be numerically equal to the dot product of 7, -5, 4 with any point on the plane, and boy, I've got choices now. I've got P, Q, and R. They're all on the plane. Which one has the most zero components and the least annoying things like negative signs that often trip me up? Q just has 2, 0, 2. So I chose him because I think he will be the easiest to work with. That equation is equivalent to 7x minus 5y minus 4z is equal to, and I'm looking over here, 7 times 2 is 14 plus 4 times 2, so I've got 14 plus 8. 14 plus 8 is 22. There we go. So if x, y, z is on the plane, then 7x minus 5y minus 4z is equal to 22. And conversely, if a triple of numbers x, y, and z, right, if a triple of numbers when substituted for x, y, and z, and here gives a true statement, then that triple of numbers describes a point on the plane.